always here you have to select or always you have to focus about the minimal cost. Okay, so this is with respect to the branch and bound algorithm. So under this, according to your syllabus, you have 3 topics. One is assignment problem, second one is Knapsack, third one is TSP. So already we have discussed about traveling salesman problem. So in today's class, we will discuss about Knapsack followed by assignment problem. Okay, then we will enter into the last module, that is NP complete. Okay, before that we will complete these 2 problems. One is waiting. Okay. So hope my screen is visible to you. Okay. So first topic is 0 by 1 knapsack problem. So 0 by 1 in the sense that hope you understand the meaning. Either you have to take the object fully or you should not consider that object entirely. So here knapsack problem you can solve it by using greedy approach, dynamic programming concepts, and the branch and bound algorithms also. But here we are going to discuss how to find out the solution for knapsack problem using branch and bound algorithms. So this is the problem given to you. So 4 objects, and the first row is the profit, second row indicates the corresponding weights of the object. The knapsack capacity or the capacity of the bag is equal to 15. Okay. And here you are going to consider 4 objects. So n is equal to 4. And here see here. So as I said earlier, branch and bound is a minimization problem. Your objective is to reduce the cost. Okay, but knapsack is a maximization problem. Your objective is to maximize the profit. At the same time, the capacity of the knapsack or capacity of the bag should not exceed the allocated weight, that is 15 kg, isn't it? That is 15 kg. It should not exceed weight 15 kg. Is it clear? So hence, in order to satisfy both the things, in order to satisfy minimization problem as well as maximization problem, here we are going to use the concept called LCBB, that is least cost branch and bound algorithms. So the abbreviation for LCB is least cost branch and bound algorithms. So for this, first you would define the lower bound as well as upper bound. Actually both are having same equation only. The equation is nothing but a summation of I varies from 1 to n pi into xi. So xi is nothing but if the object contains, if the object is included in the bag, you go to put 1. If the object is not included in the bag, you go to put simply 0. Okay, and pi is corresponding profit. So this is the summation. So both the formulas are used to find out the lower bound as well as upper bound. But here the difference is that in the lower bound, you can able to consider the fractions also. But in the upper bound, there is no need to consider the fraction. You should not consider the fraction values. Students, please keep in mind that in the lower bound, you have to consider the fraction. Upper bound, you should not consider the fraction values. Okay, so let's see what is the difference between the lower bound and the upper bound in the upcoming slides. Okay, so since branch and bound is a minimization problem, we are going to introduce negative sign in the profit. So copy the profit value, just to put a negative sign in all the profit values. You have to keep the weight as it is. Okay, so this is the assumption you made in order to satisfy the branch and bound concepts. Okay, so before forming the state space tree, first let us consider node 1. We are going to start from node 1. And initially let us consider the upper bound is equal to infinity. Okay, initially you have to consider upper bound is equal to infinity. Is it clear? So here you have to consider node 1. Node 1 in the sense that object 1 should be included in the bag. Okay. So before that, see, so you have to fill like this. The capacity of the bag is equal to 15, isn't it? The capacity of the bag is equal to 15. So you have to include the first object, whatever the weight, just I will copy and paste. Okay, so just to see the weight 2469. See the weight alone 2469. Okay, the capacity of the first object is the weight of the first object is 2. The weight of the second object is 4. The weight of the third one is 6. The weight of the fourth object is 9. At the same time, always you have to check it should not exceed the capacity of the bag or knapsack. So keep in mind that 2469. Okay. So first I can include the first object. At the same time, I have to check whether this weight is not exceeding the weight of the knapsack. The next weight is 4. I can able to include. Now the capacity of the bag is 2 plus 4, 6. Again, I can include the weight of the third object also, so 6. See here, now this is 2 and this is 4 and this is 6. So 12. So remaining space is 3 kg only. Remaining space in the bag or knapsack is only 3 kg left out. Isn't it? 3 kg left out. So only 3 kg is left out. But what about the capacity of the fourth object? 9 kg. So out of 9 kg, you are going to consider only 3 kg. But this is for lower bound calculations only. According to the 0/1 knapsack, you should not include the fourth object. So clear, this is for the purpose of lower bound calculations alone. Since we are talking about 0/1 knapsack, either you can include the object fully or you have to reject the object fully. Okay, so this is for calculations purpose alone. So the remaining weight is only 3, isn't it? So this first 3 objects already occupied 12 kg. So the capacity of the knapsack is 15. So the remaining is only 3. But actual capacity of the fourth object is 9 into their profit. So the profit of the fourth object is 18 minus 18. See here, so the profit of the fourth object is minus 18. Okay. So now write the profit at outside of each and every. Just wait. Okay. So this is profit of the first object. This is profit of the second object. This is profit of the third object. You should not write the profit of the fourth object as it is, since only 3 kg is reserved, isn't it? So do the simplification. So the answer is minus 6. Okay. So for the lower bound calculation, L cap of 1, you have to consider all the values. Fraction, you can consider the fraction values, isn't it? As I said earlier, you have to consider the fraction values when you are calculating the lower bound value. So lower bound value is nothing but, so add all these values. So minus 10, minus 10, minus 12, minus 6. So the value is equal to minus 38. So why the mouse is not working? Okay, so minus 10, minus 10, minus 12, minus 6. So the value is minus 18. But for the upper bound calculation, you should not include this value. Fraction will not be considered when you are calculating the upper bound value, isn't it? So this minus 6 is due to considering the fraction. This minus 6 is due to considering the fraction. So for the upper bound calculation, you should not consider this one. Is it clear? You should not consider this one. So for the remaining value, minus 10, minus 10, minus 12. So only minus 32. So this is the difference between upper bound calculation and the lower bound calculation. Now this is the state space tree. So write the upper bound value as well as lower bound value here. Okay, 1. So this is just like a binary tree. So either you can include the object 1 or you should not include the object 1, isn't it? So x1 is equal to 1. Let us assume that x1 is equal to 1. The meaning is that you are going to include the object 1. And next level, you are going to find out the first object. Let us assume that the first object is not present. And you have to calculate the lower bound as well as upper bound values. Is it clear? See here. So this is, see this lower bound and upper bound value is same as that of the previous one. Okay, isn't it? So here already you have considered the object 1 and you found lower bound and upper bound value. So repeat the value as it is here. There is no difference between lower bound and upper value of node 1 as well as node 2. Just repeat as it is. Is it clear? And only thing is here you have to calculate lower bound and upper bound value. So how to calculate lower bound and upper bound value? So for this, you should not include the first object. So you have to start from second object. Okay. So actually the weight of the bag is 2469. Is it clear? So the weight of the objects are 2, 4, 6, 9. You should not include the first object according to the constraints. So you go to include the second object. 4. You can include third 2, isn't it? 6. You can include that 2. See the total. So 4 plus 6, 10. The capacity of the bag is only 15. The remaining left out space is only 5. So 5 by 9 into minus 18 is included. Okay. And by using this profit value, just to find lower bound and upper bound value and include it in the graph. So this is lower bound value for the node 3. This is upper bound value for the node 3. So here you have two different nodes, from which how you go to select which node. So for this you have to consider the lower bound value. Okay, select the minimal lower bound value. So I think this one is the minimal lower bound value. See, you have to compare node 3 and node 4. Take the node which is having least lower bound, So which is having least lower bound in the sense that the node 2 is having least lower bound. Isn't it? The node 2 is having least lower bound. Okay. So there is no need to proceed from this graph. It is enough to proceed only from node 2 alone. So here you made the decision that object 1 is included. So here also you have to take two different outcomes. One is include the object 2, another one is don't include the object 2. Okay. So see here, if you include the object 1 and if you include the object 2, so the value is same. So this value is same, there is no difference in that. So just to copy and paste the value here. Okay. And now again take the knapsack. So you can include the object 1, but you should not include the object 2. See the constraint. You can include object 1, but you should not include the object 2 and compute the lower bound and upper bound value. So this is available in the next slide. Okay. See node 5. We are in node 5, isn't it? So node 4 already I discussed. So node 5 you can include object 1, but you should not include object 2. So the weights of the object are 2, 4, 6, 9. So you can include object 1, you should not include object 2. So first in the knapsack you go to put 2 kg, then you go to put 6 kg, compute the total 8. So remaining spaces, the capacity of the knapsack is 15. Okay, so the remaining weight is 7, isn't it? So 7, but actual weight of the fourth object is 9. So 7 by 9 into profit is minus 18. So for the lower bound calculations, you have to consider all the three values. For the upper bound, you have to consider only these two values alone. Okay, and this is repeated in this value is reflected in the previous graph. See here, so lower bound value is equal to minus 6, upper bound value is equal to minus 22. So again, you have to take the least. Again, you have to take the node such a way that it is having least lower bound value. So node 4 is getting selected. Okay, see here x1 is included, x2 is included, then x3 you can put two branches. One is x3 can be included, another one is x3 cannot be included. Okay, and if you include x3, this will be the output, isn't it? Minus x3 minus 32, this will be the output. And for if x3 is not included, again you have to apply the same formula and find out the lower bound and find out the upper bound values. Okay, find the lower bound and find the upper bound values. Okay, 2469, isn't it? So 2469. So here compare both the lower bound and upper bound value. Here both lower bound value is equal. Then how do you select which act as a root node? Since both node number 6 and node number 7 is having common lower bound values, both lower bound values are same, then use the logic. If you include the object 1, the weight is 2. Then if you include the object 4, weight is 4. Okay, and if you include the object 3, weight is 6, isn't it? Weight is 6. So if you add these things, 2 plus 4 plus 6, only 12 is there, isn't it? Only 12 is there. So this may not be an optimal path. So you go to proceed from node number 7. So node number 7. From node number 6, you should not proceed further. See here, why you can't proceed further means, even if you proceed, it is a time consuming process. See how we ignore this case. So similarly, you can ignore this case also. See here. See the left part of the tree. X1 is included, X2 is included, X3 is also included, and if you include X4, the capacity of the knapsack exceeding. It is not feasible to include all the object in the knapsack. See here. So if you add all the weights, it will be 2 plus 4, 6, 6 plus 6, 12, 12 plus 9, 21. So it is not feasible. You can't able to include all the objects in the knapsack. So from this spot, there is no need to travel further. No need to extract since the capacity will be exceeding the given limit. So only you go to proceed from node number 7. It's enough. So from node number 7, you can include either object number 4 or there is no need to include object number 4. Okay. So here also you have to consider the lower bound and upper bound values, and you have to select the node which is having least cost. So finally, see here. So from node number 7, we have node number 8 and node number 9, isn't it? So for node number 8, this will be the lower bound and upper bound value, and for node number 9, this will be the upper bound and lower bound value. Okay. So you have to select the node which is having least cost. So node number 8 will be getting selected. Is it clear? So node number 8 will be getting selected. So the path will be, you have to consider X1, you have to consider X2. No need to include X3, but you have to include X4. Okay. Only X3 object is getting rejected. So remaining objects you can consider. Let us see the profit and the final outcome. Hence the subset will be, okay, X1, X2, X3. We hear something cutting X4. You have to include X4 also. X1, X2, X3, X4. Okay. So if the object is included, you have to put simply 1. If the object is not included, you have to put 0. You have to put 0. So which means that X3 is not included in the knapsack. Okay. So now let us add the corresponding weight. So this will be the weight of profit of the first object, profit of the second object. This will be the profit of the fourth object. You should not include the third object since it is not available in the knapsack. So first object, second object, and fourth object. So the profit is equal to 38. So you are maximizing the profit value. At the same time, you have to check the weight also. So the weight of the first object is included, second one is included, third is not there, fourth is available. See the weight. So 6 plus 9, 15, and 15, this value should be less than or equal to the given capacity. So here it is exactly equal. Hence, this will be the solution. So the maximum profit is equal to 38. At last, you go to write the maximum profit is equal to 38, and the following objects are available in the knapsack. That is object 1, object 2, and object 4. Okay. Okay, any doubts, ma'am? Up to this, do you have any doubts? If you don't have any doubts, we will enter into the assignment problem. That is very simple. Are you able to follow me? Please use the chat box. But do you have any doubts in 0 by 1 knapsack? So this is by using state space tree, you go to make the conclusion. Okay, so in dynamic programming or greedy approach, you have used some other concepts, either which may be in table format or some other format. But here, branch and bound means branch and bound. So when the branch is introduced, so tree only contains branches, isn't it? So from the branches, you are going to bound means lower bound and upper bound. Okay. So from the tree as well as you are going to use the bound concepts. Bound concepts, you can able to make the decision at last. That's why the algorithm of the name is called as branch and bound. So why it is branch means which forms a tree-like structure from the tree-like structure. That is from the branches, and by applying some bound conditions, you are going to make the decision at last. Okay, that's why the name came. Okay, so only I received 2 replies. If you have any doubts, please put it in the chat box. Okay, then we will move to the next problem. It's called as assignment problem.